Hi, I am Hassan Al Kabir and I am the first author of the paper Forecasting Application Counts in Talent Acquisition Platforms, Harnessing Multimodal Signals Using LMs. Right now, I am working as a senior data scientist at Career Builder LLC USA. And other authors are either from Career Builder LLC Canada, and we have collaboration with one of the professors from Indiana University in Indianapolis. So the task is actually predicting application counts given that we have a job. So in job application we have multimodal data. So the main challenge is handling all kinds of data, say numerical, graph, and all kinds of data together. So that's one thing. And if we have the job application itself, I mean, if we have the job description, job title, and all the multimodal features, and if we can predict what will be the application count, that basically express how that job is organized and whether the job description everything looks good. So this actually expresses the quality of that job. So that's why it's very important in job domain to deal with this multimodal single and predict and predict that forecast. As we have illustrated some of the motivations earlier, we see that there are enough research works available for job recommendations, candidate matching, skill representation, uh, job classification, etc. But there are very limited works on predicting job application count. But predicting job application count aids in recruitment strategies, supports diversity goals, and informs promotional efforts for job postings with lower expected engagement. The main challenge here is actually dealing with multimodal tabular data. Uh, Say we have categorical, numerical, location, and graph data together, and we need to handle all of them together for job application count prediction. So that remains a great challenge. Another is complexity in entity extraction, schema matching, and feature extraction technique itself. Our approach here simplifies this feature extraction technique, which is the main motivation of our approach, and it can actually utilizes the pre-trained structure of the language models, and our method outperforms traditional feature fusion methods, achieving more accurate, streamlined job prediction count predictions. So in short, say we have multiple job features, say some textual features, for instance, job title, company name, job description. These are textual features. We can have categorical features, for instance, job type, state, channel, job level. So these are categorical features. And then we have graph features, skills to job and taxonomy tree. So multiple skills and jobs itself has some bipartite graph relationship. So we have some graph features for that, and we have geolocation features, for instance, city location, and salary is numerical feature, salary and other features, quantitative attributes. So there can be multiple types of features we can handle with at once. And our task is simple. We have application counts, which is a number, and we have the multiple job data. We want to predict that number. So that's basically a regression problem. One of our in-house model is multimodal FF, which deals with different features separately. For example, say we have text features. The text features are job title, job description, and company name. So all these text features can be handled separately using our in-house CNN-based embedding method, and we can concatenate all those embeddings together. If we have graph features, and graph features are extracted using another different research of bipartite graph representation technique. We can have embedding of skills and jobs um, from that method. We only use the skill embedding from the graph from that research here, and say for all of our skills we can use those embeddings, and we can also uh, use the location features. So we have the latitude and longitude, which are angles of a particular location, and we can convert that location into Cartesian coordinates, and we can use those coordinates as feature. We can use one-hot encoding features for categorical features like job type, job level, state, and channel, and we can convert the numerical features, say salary, into we can normalize those numerical features, and we can use those. The final feature extraction technique for this in-house model is actually concatenating all those embeddings together, and use that as feature. As I have illustrated before, the main contribution of our research paper is the feature extraction technique. We can handle any kind of any modality as text, irrespective of its modality. Say we have salary data. We can use the text of that salary uh, as text feature. We have location data. We do not need to convert that location into Cartesian coordinate. We can use the location itself as a text. We have graph data, say list of between skills and jobs. We have graph relationship, right? So for graph data, we can use skills as a list, say list of skills separated with comma, and then we can still use that as a text feature. So in that way, we can convert any modality we use uh, for uh, job application count prediction task, and we can use those as text features, and still we can predict the application count. So we have used multiple models, pre-trained models, for instance, BART, Roberta, and we can fine tune the task of JSE forecasting. And multimodal BART of our research paper basically use the BART model, and multimodal Roberta utilizes the Roberta model. The advantages is it eliminates the need of separate models for each modality, and the second advantage is pre-trained language models inherently capture the relationship among features, so that improves the prediction accuracy and reduce processing complexity. So this is these are the hyperparameters for our research paper. I do not want to go details of all the models. Actually, everything is in the paper. You can have a look, or you can ask me if you have any question. So we have actually multiple models like LSTM and spherical embedding approach, LSTM with a spherical embedding approach, and then GRU for time series forecasting, and then deep TLF, and multimodal FF, multimodal BART, attention fusion BART. That's actually another baseline methods, and we have time series models because it I mean forecasting application count is actually a time actually related to time series prediction as well, because if we increase the day, say at day one there will be some application counts, and for day three there will be others. So application count is related to how longer that job is in the portal. So that's why we compare with some time series forecasting models as well, so that we can have a fair competition. So this is the result at a glance of various methods on different day test datasets trained separately. So say we have only day one data available, and we have the train, test, and validation all from day one data. So if we train different models on only day one, what is the result? So that's how this table is generated. So from the table, it is obvious that multimodal BART has a very good performance for day one. Multimodal FF has a very good performance on day three, and for day seven, multimodal BART still performs, but again performs better. And for day 14 and day 30, multimodal Roberta has the best results. So all these models, multimodal FF, multimodal BART, and multimodal Roberta are our in-house models. So let's see the next. So here we have joint training. So we have a consolidated data set for all the days together. So that we have a single train data set, and we use days as the extra feature for all of these methods. And surprisingly, now the simplest feature extraction technique of multimodal BART has been very effective because it has the best performance for day 3, day 7, day 14, day 30, and overall by a great margin than any of the baseline methods. So the feature extraction technique is very simple, but still it can actually perform better than any of the baseline methods. So which is the surprising part of that feature extraction technique. Here we have another evaluation based on the job application count. So if the job application count is 1, we want to see for the test instances where job application count is 1, how well the prediction of all the models become for job application count equals to 1. For job application count equals to 3. So this is actually based on count based evaluation, and we still see the best performance is from multimodal BART, and this table is generated from joint training. And this is actually another evolution of the embedding itself. So from multimodal BART, because multimodal BART has the best performance, we have actually converted the embedding into a two-dimensional space, and we visualize from PCA, and we see that for every job count there is a separable. I mean, the embedding is separable. So this means that the embedding itself has some has some distinctive features that is extracted in the visualization. This is the evaluation from time series forecasting methods. Say we have day 1, day 3, day 7, day 14 data, and we want to predict for day 30. So we do not use any text feature or any kind of feature at this time. So from the previous day count, we want to see whether there is a pattern in the time series data itself, and we see that we do not have a very good score here because we are not using any text features, and the time series forecasting methods are not adaptable with text features and multimodal features. So these actually advocates that why our method is important. So we want to evaluate now multimodal BART on time series prediction as well. For instance, say we have multiple jobs, right? Job 1, job 2, job 3, and for all these jobs, if this job is kept uh, in the in the system, what will be the application count? So that is the left side. That means figure 2. Figure 2 has some time series forecasting if that job is kept for say k days. And figure 3 is how our multimodal BART predict for those kind of jobs. So it is very surprising that if we just add day as a feature, say day 3, and and we concatenate all the features together. And day 3 is also a text feature. And our model surprisingly can perform time series forecasting as well, which is very promising, because our model can use all those job features together with the baseline time series forecasting models cannot. And it can outperforms those, and it can use all those features together and still perform time series prediction, which is a great. So if we evaluate based on time series forecasting as well, our model performs the best. If you have question, you can ask me. Thank you.